Hypothalamus Artificial Intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference. Autonomous Real-Time Distributed Traffic Optimization. Conference prepared and edited by Jesus Velasquez Bermudez. His resume may be found on LinkedIn. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. The interested people must review the short conference. Sparse analytics and artificial brains. Challenge: using the Industry 4.0 environment to optimize the flow of vehicles in a large region. Solution: implement a mathematical model based on the concepts of autonomous real-time distributed optimization. Optimizing traffic light sync in a traffic system is a complex problem, primarily in complex areas with complex traffic networks. Solving the integrated problem may be impossible. Splitting the problem by zones may make easy to solve the total problem. However, the dynamic nature of the problem, and its spatial dispersion, make attempting an optimal solution utopian. The connectivity between the different problems, based on principles of large-scale mathematical optimization, ensure that the system travels the path of optimality, close to the optimal solution. Today's information capture-intensive systems, smart metering, allow optimal operating conditions to change the decisions dynamically, as traffic behavior changes in the city. From the traditional planner's point of view, the region can be seen as a single zone, which he, or she, want to optimize the traffic network, through a monolithic multi-period advanced analytical model. For a small town, it is possible that today's computers can solve the monolithic model, but for a big city it is impossible. It is possible attempt to solve the monolithic problem using large-scale optimization methodologies, based on the partitioning and decomposition of the mathematical problem. To do this, the entire region can be divided into zones, each of them associating a multi-period subproblem. In turn, these subproblems can be divided into as many subproblems as periods, to achieve the highest level of atomization. Each zone may have its own control center, which may be a computer that collects signals from the zone, and solves the problem for that zone. This approach could increase the size of the region, but in the speaker's opinion, it will still be insufficient for large regions. The Cell Transmission Model, CTM. CTM is a popular numerical method proposed by Carlos de Ganzo, in 1994, to solve the kinematic wave equation for traffic problems. CTM predicts macroscopic traffic behavior on a given corridor, by evaluating the flow and density, at finite number of intermediate points, at different time steps. This is done by dividing the corridor into homogeneous cells starting downstream. The length of the cell is chosen such that it is approximately equal to the distance traveled by free-flow traffic in one evaluation time step. The Lighthill-Witham-Richards, LWR, is a model commonly used for traffic flow based on CTM. There are three fundamental variables: flow Q, the rate at which vehicles pass a point; density K, the spatial concentration of vehicles; and speed U, the average rate of travel. The Newell-de Ganzo, ND, method is an easier alternative to solving the LWR model. ND assume a triangular fundamental diagram with only two wave speeds, UF, for the uncongested portion, and -W, for the congested portion. In a triangular curve, speed does not drop, until density exceeds the critical density and congestion begin. The density will grow until finally the traffic stops. The graph presents a sample to calibrate the parameters of the LWR model. Traffic Network Optimization Modeling. Modeling is carried out at the intersection level, with or without traffic lights. At each intersection, the flow of streets arriving or leaving must be modeled. The diagram presents the modeling in a round point. Network-level coordinated speed optimization and traffic light control. The modeling presented below is based, mainly, in the paper Optimal Network Level Traffic Signal Control, a Bender's decomposition-based solution algorithm, published in 2019. The Network Level Traffic Signal Timing Optimization problem is a mixed integer nonlinear program based on the cell transmission model that captures the fundamental flow density diagram of the CTM explicitly, by considering closed-form constraints, and thus, eliminates the flow holding back problem. The proposed solution algorithm is based on the Bender's decomposition technique. It decomposes the original MIML to an equivalent integer program, the master problem, and a MIML subproblems. A distributed optimization and coordination algorithm that can handle the computational complexity of the problem and find near-optimal solutions in real time. The figure shows the conceptual representation of the proposed methodology. The distributed optimization decomposes the network-level problem into several standalone intersection-level subproblems and solves them in parallel. The decomposition is achieved by identifying the constraints that represent interrelationships between subproblems and relaxing them. Distributed coordination pushes solutions towards global optimality by exchanging information among subproblems that share a relaxed constraint and reinforcing the relaxed constraints in subproblems by incorporating the information that is received from other subproblems in them. Then distributed optimization decomposes the network-level coordinated signal timing and speed optimization problem into several standalone intersection-level subproblems. A signal controller will be responsible for finding the optimal signal timing and the average speed of approaching vehicles. This decomposition is equivalent to cutting the links that connect intersections. In other words, the constraints that connect two neighboring intersections are relaxed, and each intersection is optimized as a standalone subsystem. To explain the process, let define V as the set of all intersection nodes in a network. Figure shows a decomposed network containing intersections N and M, belonging to V. The two intersections are decomposed by breaking the shared links between them. Intersection N is converted to a standalone subnetwork by adding dummy source cells CNO and dummy sink cells CNS to the boundaries of the intersection. The flow YN belongs to the broken links that enter intersection N from neighboring intersections. This method is incorporated in model predictive control to account the dynamic nature of the problem and further reduce the computational complexity. For those interested in the subject, the paper Network-Level Coordinated Optimization and Traffic Light Control for Connected and Automated Vehicles, published in 2021, presents the complete formulation of the problem in reference. The image shows the summary of the objective function. Finally, the diagram presents the proposed two-level structure using Bender's decomposition. Perhaps the solution time may be speed up if more levels are introduced in the hierarchical structure. In this case, it is proposed to include a level associated with the main traffic corridors that interconnect the region. It is possible to extend the proposed model using the concepts of autonomous real-time optimization. The approach may be conceived as an artificial brain composed of a network of mathematical models, general coordinator, the master problem traffic corridor coordinators intersection subproblems. The communication between the algorithms of mathematical problems must be asynchronous, operating continuously. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972, in the book Human Problem Solving wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.